Greetings. Today we're going to talk about the complex number system for college algebra. Now, numbers start out, and all numbers are complex numbers even though we don't talk about them, but then they go one of two ways. They are real numbers, which we have seen multiple times, or they are imaginary numbers, numbers that we can't see, but they are there. Imaginary numbers come in especially when we have the square root of negative numbers that we've talked about in the past. So far we've just called them non-real numbers, so if they're not real, they must be imaginary. And we state that an imaginary number is listed as the letter I in italicized. So anytime I have I can assume it's -1 underneath the square root sign. Therefore, if I were to square both sides, I see my square and my square root cancel each other, so I squared is equal to -1. We're going to need both of these definitions in order to be successful with today's lesson. So I have the definition above, and it says express each number in terms of the imaginary number I. So I'm starting with the square root of -7. That means that I have the square root of -1 times 7. I know that the square root of -1 is I times the square root of 7. And we can write it as I square root 7 or the square root of 7i. Notice that the I is not underneath the radical, so make sure that you keep them separate. It might be easiest to put your I in front so you're not accidentally putting your imaginary number underneath the radical sign. What if I have something like the square root of -16? I know that -16 is the same as -1 times 16, which is the same as the square root of -1 times the square root of 16. The square root of -1 is I, and the square root of 16 is 4. Or we write it as 4i, putting the number before the variable. Now I have negative square root of -13. So -13 is the same as -1 times 13, which is the same as the square root of -1 times 13. Notice that this negative here on the outside is not impacting anything. It just keeps following since it's on the outside of the radical. But I know that the square root of -1 is I. So this gives me -I square root 13 or negative square root 13i. Again, notice my I is not underneath the radical sign. Let's look at negative square root -64 equal to, which is also the same as negative square root -1 times 64. So again, I have this outside negative piece that's just following along. So this gives me the negative square root of -1 times 64. Negative square root of -1 is -I, and the square root of 64 is 8. So putting it all together gives me -8i. And one last one here. I have the square root of -48, so I'm splitting it up into the negatives here. So the square root of -1 times the square root of 48. I know that the square root of -1 is I. But I also see that although 48 is not a perfect square number, 48 is divisible into 16 and 3, and 16 is a perfect square number. So the square root of 16 we know is 4. So I for square root 3, or it kind of looks better to put 4i square root 3 as our final solution. Complex numbers are when we have a real number part and an imaginary part. So when I have a real number part, I can say that this A is the real number part, and the plus BI, notice how the BI has the I, that's the imaginary part. Let's add and subtract. What's really great about using complex numbers is they follow the same rules as any other variables. So when I'm adding things together, I can add like terms. Okay, so when I look at 8 plus 6i, and here I'm adding plus 3 plus 2i, I can see that I want to add 8 plus 3, which are my like terms, plus 6i plus 2i, which are my like terms. So 8 plus 3 is 11, and 6i plus 2i is 8i. 11 is the real number part, and 8i is the imaginary part, and both of these together are my solution. Let's subtract. We're subtracting two complex numbers. I can still subtract like terms. So 4 minus 6 plus positive 5i minus a negative, so here I'm minusing a negative, is the same as adding 3i. 4 minus 6 is negative 2, and 5i plus 3i is 8i. Okay. Let's multiply and simplify. I know we're multiplying because of this little dot here in the middle. I want to actually simplify my radicals first before I multiply. So I know that when I have the square root of negative 16, that's the same thing as the square root of negative 1 times 16 and the square root of negative 1 times the square root of 25. I know that each one of these square roots of negative 1 are equal to I. The square root of 16 is 4. I have the square root of negative 1, which is I again, and the square root of 25 is 5. So when I multiply all of these together, 4 times 5 is 20. And just like variables, x times x is x squared, I times I is I squared. This is where we're having to turn our I squareds into negative 1. Remember we talked about that at the first slide? So whenever I see I squared, I'm going to replace it with negative 1. So 20 times negative 1 is negative 20. Let's multiply two binomials together, or two complex numbers together. I know we're multiplying because they're squished together. So I have 1 plus 2i times 1 plus 3i, and we multiply them just as we would any other binomials. So 1 times 1 is 1. 1 times 3i is 3i. 2i times 1 is 2i, and 2i times 3i gives me 6i squared. Oh dear, I have an I squared. I know that I turn I squared into negative 1. I can also combine like terms, giving me 1 plus 5i, and 6 times negative 1 becomes negative 6 when I multiply these together. And finally, combining my last like terms, 1 minus 6 is negative 5, giving me a final answer, complex number, negative 5 plus 5i. Here I have 3 minus 7i squared, so I have this binomial squared. We know that when I have a binomial squared, it's the same thing as multiplying it by itself and then distributing. So 3 times 3 gives me 9. 3 times negative 7i is negative 21i. Negative 7i times 3 is another negative 21i. And negative 7i times negative 7i is positive 49i squared. When I combine my middle pieces, I have negative 42i. I see that I have an I squared that we replace with negative 1. So 49 times negative 1 is negative 49. I have some like terms. 9 minus 49 is negative 40. Minus 42i, completing our complex number after we multiplied. Simplify each of the following. So here I have I to the 37th power. I know that when I have a power to another power, we multiply the powers together. These are rules of exponents. I only know that I squared is equal to -1. So is there some way that I could rewrite I to the 37th as some power of 2? 37 divided by 2 is not an even number. So I'm going to write this as I to the 36th. Because if I multiply that by I to the 36 times I to the 1, when I multiply my bases, I add my exponents. So 36 plus 1 is 37. Now I can write the power of 36 using a power of 2, because 2 times 18 is 36. And now I've written my I as a power of I squared because we know what that is. Well, if I replace I squared with -1, and I have -1 to the power of 18, so if I multiply -1 times itself 18 times, I know that I'm going to end up with a +1 because I have an even amount of negatives. So -I to the 18th is +1 times my little I outside, which gives me I. Okay. Similarly, if I have I to the 58th, that's an even number, and 29 times 2 gives me 58, so power to a power we multiply. I replace my I squared with -1. This time I have an odd number of negatives being multiplied together, so I'm going to end up with a -1 as my final result. Letter C, I to the 75th. Here I'm going to take, because it's not an even number, but I know based on part A, if I were to take I to the 74th times I to the 1st, multiplying my bases together, I would get an addition of my exponents. So 74 plus 1 is 75. 74 is an even number, giving me I squared to the 37th. Replacing I squared with -1, here again I have -1 to the odd power, giving me -1 times my outside I is -I. I to the 80. That's the same thing as saying I squared to the 40th power because 2 times 40 is 80. Again, replacing I squared with a -1. We have -1 to an even power will give me a +1. I'm not multiplying it by anything else, so we're done. Those are our 4 choices when we're finding higher powers of imaginary numbers. It's either going to end up being I, -1, or 1. Those are our only 4 choices with the powers of I, no matter how high our powers go. So when you're working on your homework, note that those are the only options that you're going to end up with when I ask you to simplify I's to higher powers. Conjugates of a complex number. We use conjugates a lot in math for a lot of different reasons. Ideally, conjugates are just the exact same thing listed in the exact same order, only one is a addition and one is a subtraction. Okay. Fun things happen with complex numbers when we're multiplying their conjugates together. So part A is asking us to multiply the 2 conjugates. Notice that one is 5 plus 7i and the other is 5 minus 7i. I'm going to do a little side work. You could use this rule here to help save some time, but for those of us who need to see all of the steps, we're going to distribute. So 5 times 5 gives us 25. 5 times -7i is -35i. 7i times 5 is +35i. And 7i times 7i is -49i squared. I see that my middle 2 pieces cancel themselves out. So I'm left with 25 minus 49i squared. If you're going to use the rule, notice that we take our first term, our 5, and square it, subtract our second term, which is 7i, and square it. And we end up with the same thing. We know that we replace I squared with -1. So negative 49 times negative 1 is positive 49. And then finally adding together gives us 74. What's awesome about conjugates is we'll always end up with a number. The imaginary number will disappear. Even though it doesn't look like complex numbers with 8i and negative 8i, they are conjugates of one another because one is positive and one is negative. So when I take 8 times negative 8, we get 64, and I times I is I squared. Replacing I squared with negative 1, I have negative 64 times negative 1, which is positive 64. We're going to use conjugates to help us simplify division because we don't want to have imaginary numbers in our denominator. So we can use conjugates to eliminate those denominators that have imaginary numbers. So I'm going to multiply my denominator because I want to divide 2 minus 5i by 1 over 6 minus I. So notice I'm going to take the conjugate of my denominator, which is 1 plus 6i, and multiply my numerator and denominator, because ideally what I'm doing here is simply multiplying by by 1, because anything divided by itself is 1. Notice then that I'm putting parentheses around here because we now need to distribute. So 2 times 1 is 2. 2 times 6i is 12i. Negative 5i times 1 is negative 5i. And negative 5i times 6i is negative 30i squared. We have to do the same to the denominator. You could use our rule from the previous page, so this would end up being 6i since our second term is 6i. But if it helps you to multiply, I'll do it over here to see the long part of it. So 1 times 1 is 1. 1 times 6i is positive 6i. Negative 6i times 1 is negative 6i. And negative 6i times positive 6i is negative 36i squared. Notice our denominators disappear. All right, so I have 1 minus 36i squared for my denominator. Here I see I have a I squared, which we replace with negative 1. So negative 30 times negative 1 is positive 30. I can combine like terms. So 2 plus 30 gives me 32. 12i minus 5i is positive 7i. And I can do the same down here because I have negative 36 times negative 1 gives me 1 plus 36, which is 37. Okay. At this point you can stop, or you can separate it into two separate fractions as listed on the right. It doesn't matter to me which one you do. Okay. Our final one, we want to divide the square root of 5 plus 3i. Divided by 1 minus I. Okay, so what we want to do is multiply by the denominator's conjugate, which is 1 plus I. Okay. Now we can distribute, so the square root of 5 times 1 is the square root of 5. The square root of 5 times I is positive I square root 5. Again, I'm putting my I in front so I don't accidentally put it underneath the square root sign. 3i times 1 is positive 3i. And 3i times I is positive 3i squared. All over. Now let's do the denominator. 1 times 1 gives me 1. 1 times I is positive I. Negative I times 1 is negative I. Negative I times 1, I is negative I squared. Here I see we have two different places that we can replace with negative 1, giving me the square root of 5 plus I square root 5 plus 3I. And if I have 3 times negative 1, we get negative 3. In our denominator, I see my i's disappear as they should. And I have negative 1 times negative 1, which gives me a positive 1. Because I'm replacing this with negative 1. So negative 1 is the same as positive 1. Notice in my numerator, there's nothing that we can do to combine like terms because there are no like terms. So I just have to leave it as this huge long piece all over 2. And that is the end of our lesson on complex numbers.